So thank you very much for inviting me.
Thank you very much, Vladimir. Thank you for agreeing to give this this seminar. We are delighted to have you visiting us from Stony Brook, the Sean Yang Institute, if I remember correctly.
Yes.
And we're happy to hear about nonlinear Schroedinger equation and its history. So thank you for joining us. I'll hand over to you.
Okay, so thank you for inviting me. It's a privilege. I will be, well, my co-author Kun Hao also on the call. And I'll be lecturing. Please ask questions during the lecture, but maybe I can ask when the person asks a question. First, unmute yourself and then tell me your name and then say the question. Okay, so latest nonlinear Schrödinger equation. Okay, let me try to click. Oops. Okay, so the model has many names. Some people call it Lieb-Liniger model, Bose-Gas with delta interaction, Tonk-Girardot, and nonlinear Schrödinger. It has applications and significance in quantum optics. Actually, it was built in Amsterdam. In Amsterdam, von Druten built this nonlinear Schrödinger in optical lattice. And that's the link, by the way. If you have PDF file, if you click on the link, then the paper of von Druten will come up. So all links are like this. So first, we shall start with the Hamiltonian of the continuous nonlinear Schrödinger, which shall discretize later. So in classical case, psi is a complex function. So psi dagger is complex conjugate. In quantum case, it will be bosonic operator. So this model, and the first term is kinetic energy, non-relativistic kinetic energy, and the second is point-like interaction. Kappa is coupling constant, which will be positive for this lecture. So this is Poisson brackets. We quantize in the standard way. So this model is completely integrable. In classical and quantum case, it has infinitely many conservation laws and Lax representation. That's a link to Wikipedia, what is Lax representation. So this is Lax representation on the lattice. So I'm about to discretize. So x, continuous variable, will be replaced by n small, which is integer value variable, and delta is a lattice step. So let's move to the next transparency. Okay, so I'll be talking a lot about L operator, but I won't be talking much about M operator. The reason is because Lax representation, it follows from Yang-Baxter equation. That's a link where it's proven. So if you click on the link, then the paper with the proof will come out. So how to construct Lax representation from Yang-Baxter. So this is some notation from quantum inverse scattering methods. So L is this L operator in the quantum case. So I already considered the quantum case. And those two different values of spectral parameter. This is cross is a tensor product. And R matrix is a famous object of quantum inverse scattering method. So in this case, L operator is matrix 2 by 2, R matrix 4 by 4, and R matrix entries are R matrix are complex numbers. They're not operators, and they depend on spectral parameters lambda and mu. So R matrix by itself satisfies some cubic equation, which is called Yang-Baxter equation. And Yang himself, a long time ago, 1968, found the first solution. And first solution is here. So R matrix is I, which is square root of -1, identity, which is a four-dimensional matrix with ones on the diagonal, mu minus lambda, difference of two spectral parameters, P is permutation, and the people from computer science call it swap operator. So the same R matrix describe not only nonlinear Schrödinger, but it also describe XXX Heisenberg spin chain with spin 1/2. We'll be talking a lot about this Heisenberg chain during the duration of this lecture. So later somehow I will use this note that when for the special value of the spectral parameter, when lambda minus mu is equal to I, then R matrix turn into one-dimensional projectors. So it's degenerate, and later it will be important. I will mention this again. So wait. Okay, so this is so the model was embedded in quantum inverse scattering method by Fadeev, Sklyanin, and Takhtajan. And this is the link. If you click, then the article in Wikipedia about quantum inverse scattering method will come up. So in this lecture, I will use algebraic Bethe Ansatz, and there is some paper about algebraic Bethe Ansatz, what it is. Once again, please click on this. To orthogonality and completeness of Bethe Ansatz wave function was proven by by your faculty, Tony Dorlas, Tenius C. Dorlas, long time ago. Okay, so let's describe quantum model a little bit for quantum version of the continuous model. So the approximate L operator in the sense of the step of the lattice. So this expression is valid in linear approximation in delta, delta square, and neglected. So approximate L operator on the dense lattice, meaning small delta, was discovered by Vladimir, and Tartajan long time ago, 79. So this is matrix 2 by 2. I have a spectral parameter on the diagonal. Off diagonal, I have this kappa, and kappa is basically my quantum Bose field multiplied by the lattice step. Plus corrections from the point of view of Vladimir, and Tartajan, there was this corrections. So next transparency, we can restore all corrections and find all orders in delta. So let's go to next transparency. So exact L operator, meaning that all orders in delta. I discovered this with Izergin long time ago, 1981. That's a link to the paper where we discovered this. So this is exact L operator. It kind of reminds approximate. So on the diagonal, I gave side a number of particles with a coupling constant. Off diagonal, I have this square root of coupling constant, and then this rho. Rho is a square root of 1 plus this side psi. So it's a kind of it's some summation of all orders in delta lattice step. So this is lattice nonlinear Schroedinger. So this is L operator of lattice nonlinear Schroedinger. So this is, I mean, relates to the title of my lecture. We discretize it in a smart way, so we didn't change our matrix. Our matrix is exactly the same, like in the continuous case. This is a Young's arithmetic 1 plus permutation. So let's proceed. Well, I can map this model to Heisenberg model. If I take my L operator, the one which I described, multiply by Pauli matrix, I mean Z Pauli matrix, diagonal one. People call it third Pauli matrix. Then I will change L operator a little bit, and then I can write this in the form spectral parameter multiplied by the square root of -1. And then Pauli matrices, sigma, 3 Pauli matrices, summation with respect to K, and then S. These operators, they're written in terms of the Bose field on the lattice, like harmonic oscillators. But if I calculate the accommodation relation, this is perfect representation of SU to algebra with a spin which is negative number, negative spin. Negative spin is -2 divided by coupling constant by the lattice step. And then later, somehow we shall like to specify this spin to -1. This will be our main example. By the way, if
does this make it non-unitary to make it negative spin? This is not a unitary representation.
It's not unitary representation, that's correct. That's not unitary, but my remark is the following. Our matrix of Young's matrix is such that it commutes with this sigma z. So when I multiply by sigma z, I do not change our matrix. Our matrix is the same. And the representation is infinite dimensional, so it is not unitary. Okay, so sometimes I will be talking to language of this Heisenberg XXX with negative spin or lattice nonlinear Schroedinger. Okay, so this is the piece of quantum inverse scattering method. So usually L operator is matrix 2 by 2, so this space where I wrote L as explicit matrix 2 by 2, I labeled by 0. So this is space number 0. And the other index describe the lattice. I mean, I have many lattice sites. So this is 1, 2, L capital, the second index, label the lattice sites. So this is L operator in site number 1, then multiply by the L operator set in the site number 2, and I multiply them as matrices 2 by 2, row by the column, well, as matrices 2 by 2. So I multiplied a lot of them in all the lattice sites, which is under consideration. So I will get matrix 2 by 2, and this ABCD are quantum operators. They depend on this psi, on the Bose quantum field. So this is called monodromy matrix. This is standard lingua of quantum inverse scattering methods. It's the main object of quantum inverse scattering method. And the trace of this, trace meaning A plus D, is called the transfer matrix. So this is some lingua, some jargon of Young, Baxter, Faddeev, Shadashvili. So this construction called co-multiplication, and then this doesn't change our matrix. The same our matrix give commutation relation of these two monodromy matrices. If I take the monodromy matrix, the spectral parameter lambda and mu, then this is the same commutation relation which I wrote for L operator. So this is smart construction. Now it comes out that it's easy to invert this matrix. Inversion of this matrix, like ABCD, people in quantum groups called antipode, but it strongly reminds Kramer's formula, which is inversion of the classical matrix with the complex entries. So it does remind. So in denominator, I have a determinant. So in classical cases, normal determinant. In quantum cases, quantum determinant. Quantum determinant differs from the classical by this shift of the spectral parameter. So AD minus BC, but the second argument shifted by I. And then this matrix combination, this is Pauli matrix, and this transposition, but this is exactly the combination of matrix elements which I use in the Kramer formula when I invert the normal classical R matrix. So the main difference is this shift of spectral parameter. Where it come from? It come from this fact. Remember, when lambda minus mu, the difference of these two spectral parameters equal to I, the R matrix turned into one-dimensional projector. So all of this together help me to invert the monodromy matrix, and antipode and quantum determinants are important in the theory of quantum groups. This is like central objects in quantum groups. So let's proceed to the next. Oops. Next transparency. Okay, so this model. Somebody asking questions?
Yeah, Vladimir Evgenievich, it's me. So you're considering R matrices that have non-different spectral dependence, right? Only.
I consider R matrix, which was found by Young, which is 4x4 R matrix, which is linear function spectral parameter depends on lambda minus mu. Well, later the generalization. In the end, I will talk about generalization, but at this moment, R matrix is 4x4, the one which found by Young, 1 plus permutation.
Okay.
Okay. So this model, this model is solvable by Bethe Ansatz. So this is Wikipedia link. What is Bethe Ansatz? Bethe Ansatz, usually people who use Bethe Ansatz impose periodic boundary condition. Periodic boundary condition lead to some system of Bethe equation. This is the system of Bethe equation. So lambdas, there are several of them, similar to momenta. Later I will find the formula which express momentum of a particle in terms of lambda. Lambda is spectral parameter actually, but there are several of them. S is spin. This is my negative spin. Remember, my main example will be spin is -1. So eventually I will plug -1 here. That's it. In the right-hand side, this is -1. And in the right-hand side, I have this difference. So this is Bethe equation, which is a standard part of Bethe Ansatz. And then if I solve this Bethe Ansatz equation, I have to calculate the sum in the bottom. This will give me energy. I will write explicit form of the Hamiltonian momentarily, maybe the next transparency. So Bethe Ansatz, standard form of Bethe Ansatz. Okay, before I write the Hamiltonian, let's analyze Bethe Ansatz. So this Bethe Ansatz has some special properties. So I can prove several theorems about this system of equations. So this is system of equations should be valid for each and every k, where k runs from 1, 2, 3, 4 to n capital. So the first theorem, so if solution exists, then they are real numbers. So how I can prove that this theorem? So if solution exists, then they can be only real numbers. So this is one of the equation of the system. And then this is properties of the factors in this equation. So for example, in the left-hand side is a small, each factor is smaller than 1 when imaginary part of lambda is greater than 0. In the right-hand side is kind of the other, in the right-hand side is the other way around. In the right-hand side, factor in the right-hand side, it is greater than 1 when imaginary part of lambda greater than 0, so upper half plane. Okay, so let's have this in mind. So let's prove that all solutions, I mean, if they exist, they have to be real numbers. So if there are several lambdas. So some of them has maximal imaginary part. So let's pick that one, the one which has the maximum imaginary part. If there are several of them, then pick one of them. So let's write this equation with a k label of lambda specified to this maximum. If I have maximum, then in the right-hand side, I'm sure that this difference imaginary part is greater than 1. So the right-hand side is greater than 1. Now I look on the left-hand side. In the left-hand side, I know that it's greater than 1. So this means that imaginary part of this maximum is smaller than 0. So this consideration show me that imaginary part of maximum is smaller than 0, but this was maximum, so all of them are smaller than 0. So this is one part of the proof. Now I can consider lambda with a minimal imaginary part. Repeat this calculation, and in such a way I will be able to prove that all imaginary parts are greater than 0. So this means that each of them has to be equal to 0. So if solution exists, that all of them are real numbers. So now next transparency, let's prove that solution exists. So in order to prove that solution exists, we have to consider logarithmic form. Logarithmic form of Bethe equation. So first I take logarithm and then L, length of the lattice, theta is this expression, logarithm of that equation which we have. That this sum came from the double product, and this is integer numbers. Well, depending on the length of the lattice, they can be integer or half integer, but they have to be all different from one another. This is proven in this paper. It's called Pauli principle. Pauli principle in the momentum space, so all n's has to be different. Logarithmic form of Bethe equation. This is convenient in order to prove existence of solution. By now I know that all of them are real numbers. So how we prove existence? So we use Young action. Young action is the following: L, length of the lattice. This theta is an integral of the scattering phase. And this theta 1, and then this is integer numbers, which I saw in the previous, and the lambdas are solution of my Bethe equation. So Bethe equations by now can be considered as extremes of this action. So if the derivative, I differentiate s with respect to lambda and require it to be equal to 0, this is Bethe equations. So my Bethe equation I can rewrite in the following form: ds d lambda equal to 0. All right. So, but by now let's consider matrix of the second derivatives of lambda. So matrix of the second derivatives, I can calculate this. It has some form, and k is some positive expression. K is actually well, here's k. Here's k. So k is positive. K is positive. So by now, let's calculate quadratic form of this matrix of the second derivatives. Let's pick up some real vector, which is unrelated to lambda onto anything. So if I do that, then I can calculate the quadratic form and write it in the following form. So the first, the term is positive. L is positive, k is positive, v squared is positive. And the second term, this off-diagonal terms, I managed to combine in the following expression: positive k and the square of the difference. Quadratic form is positive. It means that all eigenvalues of this matrix of the second derivative are positive. This means that S is convex, so it has unique minimum. So solution of this Bethe equation exists and unique. So that's a proof of the existence and uniqueness of solution of Bethe equation for this specific model. Okay, so since we start talking about this matrix of the second derivatives, I can mention that it appears again later in the theory. Somehow algebraic Bethe Ansatz and quantum inverse scattering method help us to construct eigenfunction of the trace of monodromy matrix and of the Hamiltonian. And then one can calculate the square of the norm of this Bethe wave function. One can prove that this square of the norm is a determinant of this matrix of the second derivative. So this is famous conjecture of Godin, Michel Godin from Paris, I guess, from Saclay. He conjectured this in 1972, and I proved this 10 years later. So famous Godin formula. Let's proceed. Okay, so next thing which people do in Bethe Ansatz, they consider thermodynamic limits. So meaning that the length of the lattice goes to infinity, number of the particles go to infinity, but their ratio are fixed. N divided by L are fixed. So I remember Pauli principle. So all n's has to be different, all lambdas has to be different. So this difference lambda j plus 1 minus lambda j never vanish. So then I can transfer what a standard technique of Bethe Ansatz helped me to rewrite my system of Bethe equations as one linear integral equation. So this integral equation for this rho, this is the distribution function of the roots of the solutions of Bethe equation. So 2 pi rho, this k, here is k, kappa is coupling constant, which is positive integral, and the k again. So Bethe equation, nothing much surprising. It's, so this is for the latest nonlinear Schrödinger. This is latest nonlinear Schrödinger so far. But I can compare this with the continuous nonlinear Schrödinger, which is next transparency. Nevertheless, before I do that, I formulate an open problem. Remember my lecture called History and Open Problems. So far, I was talking about history, more or less. and the first open problem. First open problem, it is important to analyze this equation with the coupling constant kappa go to 0. What happened is when the coupling constant become very small, then this kernel of equation become very close to 2 pi multiplied by delta function. But if this is so, then it cancels more or less left-hand side. So this k in homogeneous term stands alone. So this means that this integral equation is singular in the limit of small value of the coupling constant. This is one of the open problems, first of the open problem. So let's see.
Can you say something about the distribution rho?
Well, this rho, one can prove that this is a positive function which is away from 0, and it's kind of a convex. So it looks like a looks vaguely like an arc of the circle. I mean, one can solve it numerically.
It looks like a random matrix eigenvalue distribution.
And actually, Craig Tracy, I will refer to Craig Tracy in the next transparency. That's true. So let's go to the next transparency. This is a similar integral equation for the continuous case. I mean, not lattice, the continuous. So the main difference is this: instead of k, I got 1. And this is famous Lieb-Liniger equation that many people wrote papers about this. So Craig Tracy, Guillaume Lang, and Prolhag, there are 3 papers. These 3 papers, once again, if you click on this, the papers will come up. Please use your PDF file which you have. Then they study this limit when coupling constant is very small. And then it's really singular. They map this to Riemann-Hilbert problem, which they solved. And the solution was the following. They got some kind of a Taylor series in square root of kappa log k, and the coefficients, which are Riemann values of Riemann zeta at odd argument. The coefficients are, distinguished objects of number theory. So for the continuous case, this was solved. So people know how this solution behave in the limit of small k, but for the lattice, it's not known. From the physics point of view, I understand what's going on, because for positive kappa, I have this Pauli principle, so all lambdas are different. But for k equal to 0, when the coupling constant equal to 0, I have Bose-Einstein condensation. This is 3 bosons, they have a condensate. So when kappa coupling constant go to 0, this is collapse of the Fermi sphere into Bose-Einstein condensation. That's the reason why it's singular, that's the reason why it's difficult to solve it. So this is, open problem number 1. It's in the PDF file which you have. So I want to proceed to the next transparency. And the answer is yes, it's clearly closely related to random matrices. Okay, so let's consider thermodynamic limit of my lattice nonlinear Schrödinger. So once again, I can say this is lattice nonlinear Schrödinger, or I can say this is xxx with negative spin. I'm mainly concentrating on the spin equal to -1. So this was energy. So in the thermodynamic limit, everything in Bethe Ansatz can be described by linear integral equation. For example, the energy of the ground state, more or less, I described this ground state, this rho, which was the subject of my integral equation, described the distributions of lambda in the ground state. So ground state was described in the previous transparency. Now excitations. So a particle, elementary particle, it has energy. This energy can be found is given implicitly in Bethe Ansatz. So it's epsilon, the energy of this excitation, is a solution of this integral equation. So the k is the same integral equation. Well, the left-hand side, the kernel of the integral equation, the same which I saw for rho. But the inhomogeneous terms is a little bit different. I have this, this is bare energy, and this is chemical potential. And also epsilon has to vanish at the integration ends, at the limits of integration. One can study this more carefully, this elementary excitation. Elementary excitation, I will talk a little bit. For example, if I make a hole in the ground state is Fermi sphere. So I can kick out one particle, make a hole in the ground state. So this is elementary excitation. Energy goes, satisfy this equation, but it's somewhat tricky. It does not satisfy periodic boundary conditions. My Bethe equation, this was periodic boundary condition. In order to construct elementary excitation, I cannot use periodic boundary condition. I have to switch to anti-periodic. This means that elementary excitation has a topological charge. It does not fit in the periodic boundary condition. I have to switch boundary condition to anti-periodic. Next transparency, more about this elementary excitation. This is elementary excitation. So from -q to q, this is lambda x. This is my ground state, the Fermi sphere in the ground state. So elementary excitation inside of the Fermi sphere, I have to make a hole. I may kick out one of the particles. So this is energy of the hole. And here outside of the Fermi sphere, I put one particle extra. So this is energy of the particle. And this is elementary excitation. So it's a hole outside of the Fermi sphere. It's a particle outside of the hemisphere and the hole inside. So, but then this is kind of serious stuff. This is really elementary particle, meaning that any energy level in thermodynamic limit is a scattering state of several of this elementary excitation with different momentum. So this is elementary excitation. Let's go to the next transparency. So I said lambda is spectral parameter. I said that it's somewhat related to momentum. So what's exact relation? What's the exact expression of the momentum in terms of the spectral parameter? So in the particle side, when momentum is greater than q, for example, my momentum, physical observable momentum, is this logarithm, which is bare momentum, and this integral theta is a scattering phase, and rho is that rho which we discussed. It's a density distribution or in the ground state. And for the whole, there's the same similar expression, but with a negative, with a minus sign. Now, this was energy and momentum of elementary excitation. How about scattering matrix of two elementary excitations? Scattering matrix, there is no reflection, only transition, and this transition, the phase shift. So the phase shift is, the phi. It also satisfies similar integral equation, the same kernel and theta in the right-hand side. So this is scattering matrix, the phase shift, the transition coefficient of two elementary excitation. But how about many elementary excitation? If I want to consider scattering matrix of many particles, then the scattering matrix of many particles is a product of pairwise scattering matrices. So, like for example, 3 particles, they have 3 collisions, so I have 3 factors. So this is actually a very fundamental fact. It's very deep. It's very deeply related to, it happens in each and every model which is solvable by Bethe Ansatz. This can be used as a definition of quantum integrability in the models of many-body quantum mechanics. If I have a many-body quantum mechanics, then the definition of quantum integrable model is such model where many-body scattering matrix is a product of pairwise scattering matrix. So let's proceed. So far, oops. Yes. Okay. So far I was talking about zero temperature. This was a solution of my lattice nonlinear Schroedinger at zero temperature. How about thermodynamics? Thermodynamics was the idea how to construct thermodynamics for Bethe Ansatz solvable models was put forward by Young, Chen-Ning Yang, and actually with a brother. So 2 Youngs, Chen-Ning Yang, C.B. Young. So this is everything described in terms of solution of this nonlinear integral equation. See, epsilon, and then epsilon also inside of the integral, but it's under the log, so it's nonlinear integral equation. And then the energy, the free energy and entropy can be expressed in terms of this epsilon. It's on the next transparency. So everything, this Young thermodynamics, Young described this, but it was mathematically rigorously proven by Tony Dorwitz. So let's go to the use application of this integral equation. So free energy is given by number of particles multiplied by the chemical potential, length of the lattice, temperature, and this integral K is my kernel, and the epsilon is solution of that integral equation. The pressure is given by similar expression, and the thermal entropy. Thermal entropy is the length of the lattice, and this expression, which is somewhat lengthy. So this was thermodynamics. Now let's come back to zero temperature. At zero temperature, of course, the ground state is unique. But so the entropy of the whole ground state is 0. But instead of the whole ground state, I can pick up block of spins. I can pick up a block of X sequential spins and try to calculate the entropy of that block. So this is the entanglement entropy. The entanglement entropy are positive because I'm considering quantum mechanics. It's not classical case, it's quantum mechanics. And one can calculate this, and it's a complicated function of the length of the size of the block. But for large x, large size of the block, it simplifies, and this entanglement entropy is 1/3 log x. This is actually it also happens in continuous case. So the same formula gives to me entanglement entropy in the continuous case of nonlinear Schrödinger. So lattice and continuous nonlinear Schrödinger has the same logarithmic formula. Okay, so the open problem is to study time evolution of entanglement entropy. People write papers, it's somewhat studied, but still it's open problem, still an open problem. There is another entropy, there is generalized entropy. Instead of von Neumann entropy, which I consider, one can also consider Rényi entropy. Rényi entropy defined like this. I think I forgot logarithm here. So I forgot logarithm here. So it's trace of a raw density matrix of these spins inside of the block, raised in the power alpha. Alpha is a new parameter. This is some positive number, positive real number. I forgot logarithm. I apologize. I should take logarithm and then divide by 1 minus alpha. So Rényi entropy also can be calculated for this lattice nonlinear Schrödinger. It also depends logarithmically on the size of the block. The coefficient depends on alpha, on this power, and it's very similar to what happened in the spin chain. For example, in the XXX spin chain, if you click on this, we solved it by Riemann-Hilbert problem long time ago, but same formula. So this is entanglement entropy, still open problem, time evolution. So let's go to the next transparency. You know what? I think, by the way, I think I lost one.
Could I just ask, this is Tom Spencer. I just want to ask, what's expected of the time dynamics? Are there some conjectures?
So time dynamics is the following. First of all, it depends on the setup. My most favorite setup, well, let's discuss. You know what? I have a feeling that I missed very, very important transparency. So after this, maybe I just go to the very beginning because I think I mishandled. Okay, so answer to your question. So there is 2 different points of view. First of all, I have a spin chain, okay? And I have a ground state. So ground state has some kind of a spin configuration, the ground state. So what I do next, I measure one of the spins. So it means I just apply projector, so spin roughly, I force it to look down. This caused some perturbation in the ground state. This perturbation, all of a sudden, it happened all of a sudden. This caused a shockwave. Shockwave goes through the lattice. So this means that if I consider some kind of an interval of a block of spins around this spin which I measured, then the entropy of this spin will increase linear in time in one dimension and then saturates. People call it Calabrese formula. Some people call it, but it was published before. So Professor O'Connor, I have a feeling that I missed one important transparency. Can I go all the way back and try to trace out this transparency?
Of course, yes.
It caused some disturbance. I apologize, but I have a feeling I missed like the central thing. It was one transparency, and I have a feeling that I missed it. With the Hamiltonian, I miss completely expression for the Hamiltonian. So it's probably I just miss. Wait, that's
at the very
one.
beginning.
So I miss this transparency. I apologize. So it's in the beginning, right? It's the beginning of the lecture. So I described L operator, monodromy. I forgot about the Hamiltonian. That's a Hamiltonian. So Hamiltonian describes interaction of nearest neighbors. This is Hamiltonian of the lattice nonlinear Schrödinger, which is also can be called XXX with negative spin, spin minus 1. So this density of the Hamiltonian is given as the sum of 3 terms. Psi is logarithmic derivative of the gamma function. And the argument J is solution of this quadratic equation. In this quadratic equation, everything commutes. So I can just use Vieta's formulas to solve this quadratic equation, put this into here. So that's a Hamiltonian. Why it is important? It's like super duper important because it was derived by Lev Lipatov. So Lev Lipatov was considering deep inelastic scattering. So in quantum chromodynamics, Lipatov considered deep inelastic scattering. So this scattering is a scattering of a lepton on a baryon. This is high energy language jargon of the elementary baryons. So this scattering of a lepton on a baryon is a sum of Feynman diagrams. So Lipatov figured out the leading contribution. So he showed that leading logarithmic approximation. Leading logarithmic approximation means, well, the scattering of the lepton and the baryon goes like this. So first of all, lepton, electron, for example, emit a photon of very high energy. This is like super duper high energy of very small size. So the size of the photon is much smaller than the size of the baryon. So this photon cut through the baryon, cut a channel through the baryon. And this also, but in a moment, I will give another answer to the question of Professor Spencer. So let me finish this transparency and I'll give another answer. So Lipatov considered leading logarithmic approximation means leading logarithmic approximation, the momentum of this photon is very, very large. So leading logarithmic approximation in the momentum of this photon. So only ladder diagrams dominate, the diagrams which look like a stairs, like a ladder. And this ladder, this is a picture of the gluon, of the quarks exchanging gluons. Just quark, anti-quark, and exchange of the gluons form a ladder. And the Hamiltonian describing interaction of these gluons is this Hamiltonian, is the Hamiltonian of this, on this transparency. So that's a link to the Lipatov's paper. So if you click, you can go to Lipatov. And except of this paper, there are many, many other publications. Actually, World Scientific, the publishing company in Singapore and Asia, they're about to publish a book about this. It will come out in March. And then also Karchemsky contributed, Brown from St. Petersburg in Russia, many, many people in high-energy physics. Well, for example, also our director of the Simon Center in Stony Brook, Alvarez Game, he published about this. And I wrote the paper with Kun Hao about this. And all of this is a part of the larger trend, a larger modern trend. So in trend in our days, people describe four-dimensional Young-Mills in terms of spin chain. So this is another phase of this description. Or for example, reference to Shatashvili. So this is the important transparency, which I forgot to mention, but let me right now give another answer to the question of Thomas Spencer. So the other answer to your question. So in here, in deep inelastic scattering, so the photon cut through the baryon. Once again, the photon is very small, and the baryon from this point of view in this setup is large. So the photon cut a channel, and then this cause a shock wave inside of the baryon, and this shock wave change entropy, and that's the time dependence of entropy, which is my open problem. That's the second answer to it. Okay, I'm done through with this.
Maybe one quick precision. When you talk about this shockwave formation and its affection of the thermal entropy, what kind of structure of the spin chain you have in mind? You have boundaries. Is it open?
Well, first of all, this is the entanglement entropy, not thermal entropy. And you're asking me about the boundary conditions?
Yes, exactly. So you have
boundary conditions. So in this setup, what I have in mind is infinite lattice. So boundaries went away. So I have, in my one-dimensional model, I have infinite lattice. Okay, in the infinite lattice, I pick up a block of spins, finite block. Inside of that block, I measure one of the spins. This causes the shock wave which goes through the block, and I calculate all the time entropy of the block of the spin because it depends on temperature. That's which I have in mind.
So this is still L and infinity limit. I see. Okay.
Okay. So by now, I want to scroll down to the place where I went through. So I just, because of my stupidity, I missed this transparency. So I just, we about to scroll down to the place where I jumped from, okay? So we saw that one. Okay. With that one, this is the, okay, done. Okay, so this is elementary excitations, scattering metrics. This is Young thermodynamics, which we discussed, thermal entropy, and this was entanglement entropy. Entanglement entropy, I think more or less we stopped here. So the history is entanglement entropy, statical entanglement entropy, which is described here, was described in other models, and then behavior of the static entanglement entropy in these models were very similar to other models. So nothing new, but the open problem is a study time evolution of entanglement entropy. So now next. Okay, so next open problem. open problem is calculate correlation function. Can we calculate correlation function? So let me remind you that right now I'm talking about so calculation of the correlation function at the x-axis with negative spin -1 is open problem, but it was solved for the positive spin, for spin 1/2 correlation function in x-axis was described, and the answer for this correlation function is the following. These correlation functions for spin 1/2 are polynomials with rational coefficients of the values of Riemann zeta at odd arguments. Once again, the coefficients are rational numbers and some polynomial. If you click on this paper, or the both Korepin paper is the first paper, and so it basically has historical value. And the Miva and Smirnov is the last one. They actually have the program, which, I mean, you can click on the program and it will calculate any correlation function for you. So if you click, those are the papers. So for spin 1/2 x-axis, correlations was polynomials of Riemann zeta. So the open problem is, can we calculate correlation for negative spin, x-axis with spin -1? Maybe it also can be expressed in terms of number series. That's an open problem. Let's proceed to other open problems. So, yes. Okay, so another open problem for spin 1/2 x-axis. Some kind of miracle happened in thermodynamic limit. So when the lengths of the lattice go to infinity, new symmetry emerge, and this is infinite dimensional quantum group. It's Youngian. It's Youngian infinite dimensional non-abelian quantum groups start commuting with the Hamiltonian of the x-axis with spin 1/2 if I go to thermodynamic limit of the infinite lengths of the lattice. This is something which appears in thermodynamic limits. So the open problem is what happened with the x-axis with negative spin. Maybe some new symmetry appears in thermodynamic limit. I don't know. Open problem. Open problem. Let's proceed to other open problem. Okay, it's not an open problem, it's a side remark. So before open problems, let's have a break with open problems, side remark. So far I was describing lattice nonlinear Schroedinger. I can call it this nonlinear Schroedinger. Some people call it Korepin lattice nonlinear Schroedinger. But there is another version of lattice nonlinear Schroedinger, which was discovered by American mathematician Mark Ablovitz. He's from Midwest, from Boulder, Colorado. So there is another discretization of nonlinear Schrödinger, which is called Ablovitz-Laddick discretization of nonlinear Schrödinger. It's actually very simple. The classical differential equation written here. This is Ablovitz-Laddick discretization of nonlinear Schrödinger. Well, it's also solvable by inverse scattering method. So I can compare L operators of Ablovitz-Laddick and the one which I explained here. They're different. Nevertheless, Tim Hoffman, he's a professor from Technical University in Berlin. He proved that Ablovitz-Laddick is gauge invariant to the one which I explained here, to Korepin. So this means that L operator can be mapped by means of gauge transformation. So classically, this is the same differential equation. Ablovitz-Laddick is the same like the one which I explained here. But the gauge matrix depends on the dynamical variables. So this means that our matrices are different. So our matrix, for my case, is the one from Young, but Ablovitz-Laddick, they have trigonometric version of that. So our matrices are different. So this is kind of exciting. Sounds like a non-uniqueness of quantization. Quantum versions also different. And then I just long time ago, there is other examples of exactly solvable models where we saw the non-uniqueness of quantization. I mean, in general, it's kind of trivial. Of course, quantization is not unique, but I mean, from the point of view of exactly solvable models, that's another example. So let's just remark. Okay, let's proceed to open problems. So more open problems. So far in my lecture, I discretize space variable x. But one can also discretize time variable t, and then I will go in such a way. I will go to double discrete. It was done. It's known in the literature. Tim Hoffman published a book about this. This is a reference to the book. So solution of this double discrete. So he described in terms of Hashimoto surfaces. But the more modern language, more modern name for these Hashimoto surfaces is tropical geometry. So that's the right-hand side. The right-hand side, this is a object of the tropical geometry. See those geometrical surfaces, which consist of the piece of the straight line and angle. Those are tropical geometry, Hashimoto surface. So they looks like walls of the buildings, and they have applications in the architecture. So some cities built out of these Hashimoto surfaces. So let's proceed to our open problems. So the open problem, first of all, more of the history. So this field of double discrete, completely integrable differential equation was developed by people, Babenko and Suris. They're both in Berlin right now. They actually work in the same place where Hoffman. So they wrote some papers where they discretize double space, space and time, both are discrete. They wrote many papers, some review, and also mention application. So what's the open problem? Open problem is quantization. So far, this double discrete only was done for the classical case. So classical nonlinear Schroedinger, double discrete, classical Korepin freeze, but nobody quantized. So quantization of double discrete is an open problem, which is kind of exciting from my point of view. So I proceed to the next transparency. So now we can keep discretizing. Now we can discretize by now the value of the unknown function. So in classical case, I had a differential equation, x and t are variables, and psi is unknown function. So I discretize space, I discretize time. I can also discretize the value of the function, of the unknown function. If I do that, then I will proceed to cellular automata. Okay, so cellular automata are studied by mathematicians mainly. So there is an article in Wikipedia about cellular automata. Also, mathematicians work on the classical completely integrable cellular automata. That's if you click here, there is several papers on the classical completely integrable cellular automata. Babenko wrote about this. Professor Takhtajan, he is also from Stony Brook, he wrote Santini, and then many others. This is actually studied subject. Studied subject. So classical completely integrable cellular automata exist. So how about quantum? Well, construction of quantum completely integrable cellular automata is open problem, but something is known about quantum cellular automata. First of all, this is a review. If you click here, so Fratelli, he wrote, there are several reviews. This is one of the reviews on the quantum cellular automata. These people who wrote reviews of the quantum cellular automata, they're experts in quantum information. So for completely different point of view. I mean, comparing to Babenko and Hoffman. So Babenko and Hoffman was pure mathematicians. Those people who wrote reviews on quantum cellular automata, they're just quantum information people. So, of course, Toft wrote the book, reference. I'm mainly excited about this one, the special case. This is Pirolli. Pirolli wrote a paper that if you click here, you will find it. So he took special case of quantum cellular automata, which he was able to solve analytically. Analytical solution of Pirolli given by matrix product states. I mean, he didn't formulate Bethe Ansatz, so he didn't relate this to Young-Baxter. So he solved it analytically, implicitly, relatively implicitly in terms of matrix product state. This gave me hope because some time ago, I wrote a couple of papers where I argued that matrix product state can be reformulated in terms of algebraic Bethe Ansatz. So anyway, the open problem in here is construction of quantum completely integrable cellular automata with some help from the literature. So let's proceed to the next transparency.
By reformulation of MPS, you mean computing the MPS overlaps with beta states? This is what is done in defect systems, for example.
Can you repeat this? The last sentence, just speak slowly because I'm missing the words.
Okay, what I mean is that when do you talk about MPS reformulation for the Bethe Ansatz, you mean computing overlaps of MPS with some...
You know, first of all, these two last links are my papers. So we just, I mean, what I wrote this in the beginning of the lecture, this monodromy matrix, product of L operators, this is construction of matrix product state. So what I wrote the paper where I pointed out that construction of quantum inverse scattering method, this is matrix product state. Just look into here.
Yeah, I'm just precising what do you mean by reformulation, but okay.
Just click on the transparency. click on the link. You should have you know, well, I mean, identification. It's more like identification. So let's go to the next transparency. Okay, so far I was talking about nonlinear Schrödinger. Of course, there are related models with similar problems. For example, Sine-Gordon. In Sine-Gordon, there is a reference of my old paper, 1992. We formulated latest nonlinear Schrödinger in the sense we only discretize space variable. And also, I wrote a book where there's chapter 8, which is about latest nonlinear Schrödinger, latest Sine-Gordon. Also, I wrote a book about Fermi-Hubbard. Fermi-Hubbard in one dimension, solvable by Bethe Ansatz. So one can formulate algebraic Bethe Ansatz, and one can formulate similar problems in Fermi-Hubbard. So the last transparency of my lecture, references. Well, I mean, you have the file, so you can read the references. So that's all I want to say. That's the end of my lecture.
Okay, thank you very much. Questions? We are open to questions.
Well, 2 questions.
I mean, can I ask you your name?
Werner Nahm.
Werner Nahm, yes.
Yeah. One is you talked about different possibilities for quantization.
Yes, let me come back to this. Let me come back to the transparency. Okay.
And
yes, here.
Yeah. So is there some mathematical idea how to classify all possible combinations?
You know what? I will put this in the category of open problems, because so far I have just experimental setup. So, I mean, all my life I was thinking that Ablovisladik discretization of linear Schrödinger is different from mine. I saw that Korepin is one discretization, this is another. And then all of a sudden I found that paper by Hoffman, that one, where he proved that they're gauge invariant. But then I was surprised, our matrices are different. So this is just kind of experimental thing. Please click also on the last transparency. The massive steering model has its equivalent to quantum Sine-Gordon. It has some kind of standard quantization. Nevertheless, long time ago, 1980, I solved by Bethe Ansatz massive steering model, and for large value of coupling constant away from perturbation region, I found another quantization which is fully self-consistent. It's positive, scattering matrix, everything satisfies all the axioms of quantum field theory, just different quantization. So it's what I'm telling to you, that this is more like a set of experimental facts. I don't have a good mathematical formulation. So I would rather set this into the category of open problems.
Mm-hmm. Thank you. Second question, for the correlation functions for negative spin, are some correlation functions known, and does one know what the numbers are which appear?
Well, something is known, not correlation functions. You know what? In order to calculate correlation functions, people first calculate norms of the wave function. So norm is given by that determinant. Okay, the next thing, people calculate form factors. Form factors, well, in the language, I mean, there's some kind of an internal definition of the form factor inside of quantum inverse scattering method and algebraic Bethe Ansatz. It's called Slavnov formula. Well, you have the name, Slavnov. So Slavnov formula is the following. We take eigenvalue of the Hamiltonian in terms of algebraic Bethe Ansatz. So eigenvector, you remember B, with arguments of B satisfy Bethe equation. And then I squeeze it, sandwich it, take a scalar product with some other vector, which is not eigenvector. And those usually called form factors loosely. But those in the continuous and in the discrete case, we can express as determinants. And this is just important step. But okay, short answer to your question is no. So I can't write any correlation function right now, but there's some intermediate steps which were used in the evaluation of correlation function for XXX spin 1/2 already there. So it's like halfway through on the technical side.
And what are the numbers there? Are they again zeta function or something different?
No, it's open problem,
Okay, thank you.
Well, I'm not even sure that this is, you know, number theory is big stuff. So I mean, for spin 1/2, the fact that correlation and the x-axis with spin 1/2 are polynomials of Riemann-Zeta at odd arguments came as a surprise. I kind of believed, some time ago, people thought that they finally accomplish a calculation of the correlation function x-axis spin 1/2. And the answer was given in terms of multiple integrals, which look horrible, which looks like Feynman diagrams. Okay, but then, you know, somebody actually calculated those integrals. And then the answer surprisingly come as these values of Riemann-Zeta at odd arguments. Of course, this is like a great object of number theory. So like one great object should be related to other, but I cannot give you hand-waving arguments why it should have been the values of Riemann-Zeta. So I believe number theory is like the center of mathematics. So all the correct answers finally should be expressed in terms of number theory. But this is some kind of philosophy, you know. That's all. I don't have anything else to say.
Well, for these multiple integrals, at least one is in some countable domain of periods, in the sense of conservation. And the question was, would one be in the same domain also?
Well, I mean, I noticed that Dirk Kramer from time to time come from Berlin to Dublin and give lectures. So all my work about this x-axis with spin 1/2 Riemann-Zeta was motivated by his work, because Dirk Kramer, he's calculating Feynman diagrams in time in 5⁴, and he expressed everything in terms of number theory. So my model, x-axis spin 1/2, is a toy model of Dirk Kramer, and Dirk Kramer is a full quantum field theory. So this is, of course, within the realm of quantum field theory. So I think philosophically, this should be covered by Dirk Kramer.
Yeah. Well, thank you very much. That was very enlightening.
Of course.
Sorry, can I go back to your discretized Hamiltonian again?
Okay, wait.
I think it's the previous. Yes,
it's
this.
the very beginning, but I have to click one by one. I'm sorry.
No, it was the one that you had. It was the discretized one that you had just in that previous transparency.
You mean double discrete? You mean double discrete?
Oh no! Well, what I'm confused about is.
So let me go to the Hamiltonian. This one.
Well, that one as well, but this one is in the kappa b equal to 0 limit. Is that correct?
No. This is the Hamiltonian with kappa coupling was positive. This is for positive kappa.
Positive.
This is positive kappa.
It was in your nonlinear Schroedinger equation. You have 4 copies of psi. The Hamiltonian has a phi dagger psi dagger psi, and then a psi dagger.
Right. In the very first transparencies. Yes. Wait. Oops. Yeah.
So if we look at this very first transparency, what are you? I thought you were discretizing the variable x.
Well, I mean, let me say something. So if I just discretize x and write this expression in terms of discrete x, just replace x by discrete and replace derivative by the difference, then yes. I will get a model which is not integrable. This is not integrable model. This is discretization, but it's not integrable. So this means that if I just straightforward replace the derivative by the difference, this I get not integrable, meaning that in that model, when I send step of the lattice to 0, there will be phase transition. And this is not an approximation. This is not an approximation. If I replace the derivative by the difference, it's not an approximation, because I kill all the conservation laws. I kill Lux representation, I kill Young-Baxter, I kill all destruction.
But there is no unique discretization of that Laplacian.
That's true. There is no unique discretization. So far, I showed you a couple of the experimental data. So you know what? When we started this work, we imposed 2 constraints on us. First constraint was the following. So on the lattice, I want to get integrable model. This is pretty severe constraint if I want to discretize it, but keeping integrability. Then us, Izergin Korepin, we also impose another constraint, the second, even much more severe constraint. So we want to keep our metrics the same, continuous, and on the discrete the same. So exact R metric, exact the same Young metrics. I think under these constraints, it will be unique. This discretization will be unique. Okay. But then, to my surprise, Ablovitz logic, they don't pay any attention to our metrics. They don't care about our metrics at all. They just discretize. and his discretization are very nice. It's very cute. It's very neat. It's very simple, but it happens to be, gauge invariant to mine. So I'm kind of surprised.
It looks like it would have a very different continuum Hamiltonian, because it looked to me like it had a derivative in the fourth order theorem.
Well,
that it's not upside dagger, upside dagger, upside. It has a derivative on one of them.
You want to go to Ablovic-Sladik? Let's go to Ablovic-Sladik, because I think I disagree with you, but let's look at the Ablovic-Sladik. So, yeah. Wait, this is Ablovic-Sladik. So
yes.
Derivative is the left-hand side.
Yes, but look at the psi n plus 1 psi n.
Well, but the second bracket, this is second derivative. This is just n plus 1 and minus 1. This just go to second derivative.
Yes, but it's in the fourth order. It's in the interaction term.
Well, but this psi should be renormalized and rescaled. After rescaling, this term will get the delta, some power of delta. So this will go to 0, because I have to do some rescaling if I want to go to continuously.
And the rescaling will affect the time as well. Okay.
Well, remember in the beginning I have this kappa, which was psi multiplied by delta. So this is actually kappa. This is not psi.
Okay. Yeah.
Okay. So sorry for confusion. The notation.
No, it's interesting.
Notation from other papers, and everyone had different notations.
Okay.
Yes. More questions? Comments?
I have a question. Can I?
Please.
So I was wondering, so if there are higher derivative deformation of your lattice model that preserve the integrability?
Well, I mean, first of all, I can go to the continuous case, right? Let's go to continuous, transparency number 1. And then, as I said, there are infinitely many conservation laws. All the conservation laws has high derivatives, So this, when I write L matrix, monodromy matrix, I also can talk about high conservation laws. So short answer is yes, because what I'm doing is also later discretization of all of those high conservation laws, which in the continuums they had high derivatives. And then by now, if I take my monodromy matrix, trace of monodromy matrix, put this in the Taylor series and lambda, I get discrete version of those conservation laws, which will be answer to your question. So the short answer is yes.
Okay.
Through high conservation laws.
Yeah, there are also analogs in the Yang-Mills theory, like n equals 4, and this is what Vladimir Evgenich was meaning in the continuous limit, when you can have a relation to XXZ chain.
Well, first you can call me Vladimir, because we in the West, I mean, Vladimir Evgenich go inside of Russia, but we're not inside of Russia right now. So in the West, it's just Vladimir. Yeah, okay, so supersymmetric Yang-Mills is very important, very close to this. Like, for example, Kazakov wrote many papers about XXX with negative spin, and this XXX with negative spin by now is a standard part of this modern trend of description of 4-dimensional supersymmetric Yang-Mills by spin chain. This is just an example, what I will explain.
Yeah, I just maybe wanted to make a brief comment regarding the previous question on the relation to number theory and others. For example, it just appears what Volodya was mentioning in the overlaps of matrix product state with certain beta state, which is in turn used for the computation of the so-called conformal field theory 1-point functions, and 2-point functions. Remarkable point is that from the field theoretic perspective, these overlaps lead to multiple integrals, which almost very closely arise in what is called elliptic genera, or relation to multiple polylogs. So there is quite a strong indication that there is a relation to number theoretic connection, but people just and in these settings, which are integrable settings, which are called defect integrable CFTs or boundary integrable CFTs. The point is that those integrals that arise, they are very close to what people do with computation of the sunrise diagrams. But the problem is that there are special function prefactors, which for the moment do not allow to actually to compute those integrals. But it definitely does involve elliptic multipolylogs and others.
So thank you very much for the comment. Okay, so comments, questions?
Yeah, I have one further question. This is a very elegant condition that you say for discretization you want to preserve the R matrix. Does it work for other models?
It works for Saint Gordon. I sent my book. I sent a file of the book to Professor O'Connor, so you can get the file of the book. And there is like chapter 8, which is called the latest models. So it works for nonlinear string. It also works for Saint Gordon. Saint Gordon. So far, we didn't try others, but I mean, for sure, I'm sure that this is nonlinear Schroedinger and Saint Gordon.
Thank you.
Of course.
Very nice. Other questions? Paul, do you want to ask anything? Or are you feeling you happy? Okay. If there are no further questions, we can thank Vladimir again, and I can stop the recording. We can go to a more casual mode. Okay, so thank you for a superb lecture, and I will stop the recording.
Okay, and I escape the full screen mode because somehow